Hi, in this video, we'll take a look at a method that is used to accelerate the inference on LLMs, and it's called a speculative decoding. Let us try to understand the problem first. We need bigger LLMs so as to be able to model the language better. Bigger LLMs means that it has more parameters, and more parameters that means that it has more size. More parameters also means that the model is now representationally more capable in terms of understanding the language. But the size has also increased, right? If you think of how LLMs are run on the hardware, or how any machine learning model is run on the hardware, for example, the GPUs, we first have to load the model onto the VRAM, and then the model has to travel to the L1 cache in the compute units. However, this travel from the VRAM to the L1 cache um, becomes very significant for larger LLMs because you have to keep loading more and more onto the compute units, whereas the bandwidth that is used to transfer the data is actually limited. So for larger LLMs, you would have to do more transfers from the VRAM onto the compute units, whereas for smaller LLMs, you would have to do a fewer number of transfers, and therefore the time for inference on larger LLMs is higher than for smaller LLMs, which basically means that if you're using a larger LLM to generate tokens, for example, you're chatting with an LLM, you would see there is an increased delay when you're using a larger LLM compared to a smaller LLM. But what if we could use the decreased time that a smaller LLM offers us without losing the accuracy of the larger LLM to predict the next token? Now, that is what this paper and this video is about. So the presentation goes as follows. We'll first take a look at what speculative decoding is to a more take a closer look at the speculative decoding algorithm. We'll go over the proof/intuition for why speculative decoding decreases LLM calls per token. And lastly, most importantly, we'll see why speculative decoding does not alter the output probability distribution of the tokens. Now, this is a very cool method, and it is cool because we don't have to change the model architecture. We don't have to do any kind of pre-training or fine-tuning. All we have to do is bring in a smaller LLM so as to be able to speed up an existing LLM's token generation process. So the smaller LLM that I've been talking about is denoted as MQ, or the approximation LLM in the paper. The larger LLM, or the target LLM, is denoted as MP. The approximation LLM for a given time step t, given the context x until t, has a distribution of q of x given x until t. The output probability distribution of the target LLM is denoted by p of x. And also we drop the t subscript uh, when understood as they do it in the paper. So now the process is as follows. For any given time step t, the approximation LLM predicts a token xt. The target LLM also predicts its output distribution. If the target LLM thinks that the token generated by the approximation LLM um, is likely, so that is when we are going to accept it. So that is this path. This is the case where the target agrees with the smaller LLM that the token generated by it is likely. That is cool. But what happens when the target LLM does not think that the token generated by the approximation LLM is as likely? That is the case when Q of X is greater than P of X, right? So in that case, we land in a scenario where we perform a random experiment, more like a coin toss, a biased coin toss. And after that coin toss, we still have some chance of accepting the token that the approximation LLM has predicted at that time step, even though the target LLM thought it was not likely. And the chance is given by P of X over Q of X. So we perform a random experiment with the probability of acceptance equal to P of X over Q of X. We accept the token generated by the approximation LLM. Now, in the random experiment, we could also get a rejection. the rejection probability is 1 minus the acceptance probability, and we land here. In this case, we define a new distribution called as the P prime X distribution, and we sample a new token from it, from this new distribution altogether. Just to summarize, the approximation LLM tries to predict a token. The target LLM validates it. In case it thinks that it is as likely, we accept the token. In case the target LLM does not think that the approximation LLM's prediction was as likely, then we kind of perform a random experiment. And in that random experiment, we have two outcomes, one in which we still accept the token and one in which we reject the token. Now, in the case when we reject the token, let's talk about this P prime X distribution. The P prime X distribution is defined as the normalized probability distribution between which is the normalization happens over the difference between the target LLM's output distribution and the approximation LLM's output distribution. So that is this part here, P of X minus Q of X. And we are performing this max operation with a zero. So in cases where Q of X is greater than P of X, that is where maybe the approximation LLM is making mistakes. We simply assign a zero probability. So we really would like to accentuate the areas in the probability distribution where the target LLM is higher than the approximation LLM, and we would like to sample from that. So that is the main control flow for speculative decoding. And one very important thing here to note, as a side note, maybe for implementation, is that the approximation and the target LLMs should have the same tokenizer and the same vocabulary. Otherwise, it's going to be difficult to compare the output token distributions. Okay, so let's take a look at how this process looks like in real time from this illustration taken from the paper. And so in the first time step, after giving the start of sequence, the approximation LLM predicted the word Japan, and the target LLM accepted it, so it's colored green. The next one was predicted as apostrophe accepted, S accepted, benchmark accepted. The word bond was not accepted by the target LLM, and the word itself got rejected. So we sampled from this new distribution, P prime X, and we got the word N. So note that in the cases where we have green here, it could have been accepted because the target LLM thought it was as likely, or because we did the random experiment and still ended up accepting it. In either case, the word that is being predicted by the approximation LLM, when it's accepted by the target LLM, is colored as green here. And when it's rejected, it's colored as red. And when we sample from this new P prime distribution, we have this blue color here. So we sample from we sample from this approximate distribution, keep sampling until we have a rejection. When we have a rejection, we sample from this P prime X distribution. That is all for now. In the next video, we'll take a closer look at the speculative decoding algorithm. Thank you.